Also, I record these sessions. I'm going to go ahead and turn my webcam off now that you've had a chance to see me. It tends to be a big load on the computer and slows the software down a little bit when you have the webcam open, so I typically don't leave it on.
Okay.
But I do record all the sessions, and I'll make a recording of this session available to you a couple hours after the session. And it's like a YouTube file where you can fast forward, pause, rewind, stuff like that.
Okay. I have a lot of stuff.
How would you solve that?
Solve that?
Mm-hmm. Are you solving log equations yet?
We have a test on it pretty soon.
Okay. Well, I need you to give me some problems because I don't have any idea of what degree of difficulty you're in logs. So if we want to be more precise, you need to give me the problems that you need to do.
Okay. How do I write on the thing?
Just, you don't, just read it and I'll write it.
Oh, okay. Log base of 10 parentheses 100 and then an arrow to the 100 equals 10 x.
Like this?
The x is up on top of the 10. To the power of the 10. For the x.
Okay, so you said log base 10, which is common log, so I don't need to write the base. The argument is 100. Are we trying to figure out what that is? When you say arrow, do you mean that?
Yeah.
That means implies, but that's not part of the equation. So if I wanted to know what the log base 10 of 100 is, I would say, well, let's let it be x. And now, to solve this, I have to put it into exponential format, which is to say 10 to the x power equals 100. What is x? 10 to what power would equal 100?
10. Or 2, I mean.
2. So, whenever you have a logarithmic expression, such as that, the way you convert it to an exponential expression, which is usually the way you solve the equation, is the way I like to remember it is you take the number on the far left, raise it to the power of the number on the far right, because logarithms are exponents. So that has to be 10 to the x equals the argument, 100. And now I can solve this. I know that x equals 2.
Okay.
Okay? What other ones do you have?
Um,
Let's just talk about logs for a
let's
moment.
see.
Okay? Let's make sure you understand the basics of logs. All logs conversations start out like this. That is an exponential expression. Example would be 8 equals 2 cubed. Okay? What is the logarithmic expression of that? Of y equals b to the x.
It would be log by equals x.
Yeah. And notice that if I'm going the other way, I take the number on the far left, b, raise it to the power of the number on the far right, x, and it's equal to y. So you want to be able to go back and forth between these two. So what would the logarithmic expression of 8 equals 2 cubed be?
Log 8 equals 3.
Okay, good. So you understand that. And you've undoubtedly been through these three rules. The log of a times b is equal to what?
I don't know.
The log of a plus the log of b.
Those.
These are three of the most important rules regarding logs. The log of a over b is what?
Log b m minus.
It's the log of a
log
minus the log of b. And then finally, the third most important rule is the log of a raised to the b power is equal to b times the log of a. And this one's huge, because this is the one that allows you to solve for exponents that are variables. So these three rules are gigantic for solving log equations. But I don't know where you're at in logs. You could be halfway through logs, you could be 90% through logs. So unless you give me problems that you're supposed to be working on, I won't know where to begin.
Let's do 10 to the third power equals 1,000.
And what are we supposed to do with that? What are the instructions on it? Put it in log format? Okay. What is it?
It'd be log 1,000 equals 10.
Remember that the exponent is always on the other side of the log. In other words, the moment you tell me that, I know that the log is equal to 3, because logarithms are exponents. So the other two numbers, where's the 10 going to go? As the base. And the 1,000 goes in the argument.
Okay.
So it's like that. Notice that if you gave me the log expression, I could tell you that 10 to the third equals 1,000. All right. What else you got?
4 equals 1/2 to the second -2 power, I mean.
Okay.
-2.
Okay.
Hold
on. You saying 4 equals 1/2 to the -2 power?
Yeah.
That's not a valid equation. Oh, yes it is. Excuse me. Yeah, oh, I'm sorry. It is. Okay. So, let's start with log is going to be equal to -2, right? So where do the other two numbers go?
Base of 1
Base
half.
always goes down there. And the base is always this, what's being taken to the exponent. So that's equal to 1 half. The only other number left is 4.
Okay.
So that would be the logarithmic expression of this exponential expression. Do you have any homework that you need to do in this chapter?
Yeah, I'm looking at stuff from homework and everything.
Okay. Let's just start with problem 1 on your homework and go through and do them all.
Okay.
Unless you know how to do most of them, and then let's just look at the ones that you don't know how to do.
Okay, let's do log base of 5 2 plus log base of 5 6.
Okay, now we're going to use those rules, these 3 rules. What we're doing is compressing. In other words, when you go this way, you expand. When you go this way, you're compressing. Well, we start off here with 2 logs that are being added. So we're going to use this rule right there to turn it into the log of 2 things being multiplied together. So what would that be?
It would be log 5 2 6.
2 times 6. So in other words, it's the same thing as the log base 5 of 12.
Yeah.
Okay? What else you got? That's pretty much all my tutoring is I'm not generally like your teacher in the fact that I'm not going to lecture the subject material to you. What I'm going to do is help you solve problems. Problems that you either need to do for homework or review for a quiz or whatever. The key in math is solving problems. I could lecture to you for an hour about logarithms, but that wouldn't guarantee that you learn anything. Whereas if you and I work on problems and I try to get you to the point where you can solve the problem, then you're going to learn it.
Mm-hmm. Okay. Well, can we do word problems?
Sure.
Okay. It says, write an exponential equation to model each situation and solve. Approximately 156 million record albums were sold in 1982. Albums have continually decreased in sales at a constant rate of 7.9% per year due to new technology. If sales continue to drop at this rate, in what year will 100 million records albums be sold?
Did you say 156 million or 156,000?
Million.
And we're shooting for 100 million?
In what year will 100 million record albums
Okay.
be sold?
So first of all, we need the general equation of exponential decay. Well, the amount is equal to the starting amount times 1 minus the rate of decay to that power with t being in years after 1982. Well, if I fill in everything that they're asking for, they want this amount to be 100,000 or 100 million. So if the final amount is 100 million, that has to equal the starting amount, 156 million, times 1 minus, this is in percent, so I need to convert it to decimal. So it's 1 minus 0.079%, which puts it at 92.
We were using A equals PE
to the K
power
cube.
of RT.
Okay. So they're using continuous decay.
It was P right there on the A instead of the A.
Right. P being the starting amount. I use A sub 1 because this is always whatever you started with, and this is what you end up with after T years. So the equation is only moderately different. It's E to the 0.079 T
Okay.
What's the next step to solve this?
I don't know.
Let's talk about solving exponential equations before we go further. If I said 10 equals e to the t power, that's not an algebraic equation. That is an exponential equation. I can't use algebra to solve that. I have no algebra to solve that. However, with logarithms, I can solve it. How? Because if I take the log of both sides, which I can do, you can do anything you want to one side of an equation as long as you do it to both sides. Now, the right side of the equation, I can take that t and stick it down in front of the log based on that rule number 3. See my rule 3, the log of a to the b power is equal to b times the log of a? That rule is what allows us to solve exponential equations like this. Well, the natural log of e is 1. So t equals natural log of 10, which is just a number you can get out of your calculator. So that's the way I solve all exponential equations, is using that technique. So the first thing we need to do is to try to isolate this part of the equation, e to the 0.079t.
So we have to put a natural log?
Not yet. Let's try to get rid of this coefficient. First of all, I can lop off 6 zeros and 6 zeros. Now I can divide both sides by 156. So I have 100 divided by 156 equals e to the 0.079t.
Okay.
Well, my variable is in my exponent. I can't solve this algebraically, but I can solve it by taking the natural log of both sides. After I've taken the natural log of both sides, I can bring this exponent down onto the line of the equation, like that.
And
Well,
you could get rid of the natural log e.
Natural log of e is 1. The log base b of b, in other words, this is always 1. The log base b of b, that's equal to 1 no matter what base it is. And the natural log is base e. So when we take the natural log of e, we're really taking the log base e of e, which is 1. So now I can just erase that or replace it with 1. And now I have an easy solution for t. T is equal to the natural log, this is just a number, divided by 0.079. Now,
And
it needs to be negative. That general formula, the general formula you gave me, where the amount is equal to PE to the RT, in our case we have decay. We have not appreciation, but depreciation. So R is negative 0.079.
So we just change it to that?
Yeah, just change it to dividing by a negative, because this natural log is going to come out to be a negative number. When we divide by negative 0.079, we're going to get a t that is in years.
Mm-hmm.
Do you know how to get this on your calculator? To take the log of 100 divided by 156, and then divide that answer by minus 0.079.
Natural log. Okay, hold on.
Let me get my calculator out and do it with you, just so. What kind of calculator do you have, Caleb? Is it a Inspire?
It's a TI-84 Plus.
Okay, it's the TI-84 then. Okay.
Yeah.
Okay, so let's see.
I got 5.63.
Yeah, that makes a lot of sense. T equal 5.63 years. That's how long it will take to depreciate from 156 million to 100 million at a rate of 7.9% per year, which means it'll be 1988. Since you got 5 and change, it's going to be 1988 when they only sell 100 million records.
Mm-hmm.
All of these word problems are going to be solved exactly the same way. You're going to end up with an exponential equation where your variable is in the exponent, and in order to solve them, you're going to have to take the log of both sides so that you can get that variable out of the exponent. Say I wanted to know what the answer to that is.
Mm-hmm.
How would I solve for x? I know x isn't 3. I know it's not 2. It's somewhere in between 2 and 3, right? 2 cubed is 8. 2 squared is 4. So it's got to be a number between 2 and 3. I don't have any algebraic way to solve for that. How do I solve it using logarithms?
Put log in front of each one.
So take the natural log of both sides, and then bring the x down in front. So I have the natural log of 7 equals x times the natural log of 2. So x would equal the natural log of 7 divided by the natural log of 2. Now you still have to go to your calculator to get those numbers, but at least we have a way of solving it with logarithms. We don't have any way of solving it without logarithms. And you could try all day in your calculator and you're not going to get that solved without using logs. How about log equations? Have you had anything that might have looked like this?
Let me look through my stuff. You mean?
This is a typical log equation where you have to solve for x. And in order to solve for x, you kind of have to use all of the properties we've talked about so far. You have to compress it, first of all. Then you have to turn it into exponential format next. And then you will have a quadratic that you have to solve. I don't want to get into this if you haven't had it. You'll be getting it. If you haven't had this yet, it'll be coming up soon, because logs are only about a 2-week subject. You're only going to stay in logs for a couple of weeks, I'm guessing.
Okay. Well, I have more problems.
Good. Let's do those. It's always better for you to bring the problems.
I'll just do this whole sheet.
Do you want to take a picture of that sheet and send it to my email, and then I can bring it up on my computer screen?
Sure.
Do you know how to do that? Let me write my email. Most teenagers are pretty familiar with how to take a picture with their camera and send it to email. If you hold it about a foot away from the page and make sure you have decent light and hold it steady, it should be a document that I'll be able to read when I get it on my email. And then we can just do the problems from that. That's what most of my online students do, is they send me the material they want to go over as a picture that they've taken in advance of the session. Unless I have the same book, I might have the same book. Are these problems from your algebra book?
I have a sheet.
Okay, that your teacher gave you?
Yeah.
Now, why don't you try taking a picture of that and sending it to that email?
Okay. I can't see the email anymore.
Oh, sorry. Covered it up. Did you send it yet?
Yeah.
Takes a little bit of time when there's an attached document for me to get it. Why don't you, while we're waiting for that, go ahead and read the first problem or two on it, and we'll start.
Okay. You have inherited land that was purchased for $30,000 in 1960. The value of the land increased by approximately 5% each year per year. What was the approximate value of the land in 2010?
Okay. In this, we're going to use y equal PE to the RT, and R is going to be positive.
Okay. So it would be Y would be
the amount they're seeking. In other words, we want to know what happens to the $30,000 when it is increased at 5% annually, continuously compounded. So the P is the original, the 30,000. E to the 0.05t, and t is 50. Because it's 50 years between 2010 and 1960. So in this problem, you really don't have to solve much. There's no logarithms required because the variable is already on the algebra line, and everything else is just a constant. So take, what's 50 times 0.05? 2.5. So it's 30,000 times e to the 2.5. What is that number?
365,474.82.
That's pretty good growth. That is almost 10 times growth on your money over 50 years. Okay, I got your email. Let me open it and pull up this document. Okay, let's look at 3.
Okay.
This equation you've written right here, 5,000 equals 2,000 times e to the 10t. It's almost right, except it's 10%. You have to make that a decimal. So it's 5,000 equals 2,000 times e to the 0.1t.
Okay.
Divide both sides by 2,000. That's always the first step. What's the next step now?
Put in natural log.
Not put it in. Take the natural log of both sides. Now on the right side, it allows me to bring down the exponent, all of it. Natural log of e goes to 1. So I've got natural log of 5/2 divided by 0.1 equals t.
Okay. You want me to put that in?
Yeah, if you need a precise answer right now, that's going to be it.
$9.16.
What is it?
9.16.
Okay, that sounds reasonable. 9.16 years, and it takes about 10 years for money to go from 2,000 to 5,000 at 10% compounded continuously. Now, let's talk about compounding. There's 3 different formulas for compounding interest. One is this one. Another is this one. And the third one that we've been using is that one. This is continuous compounding. This is annual compounding. And this is more often than annual, with N being the number of times per year you would compound it. In other words, if something's being compounded yearly, we're going to use this top formula. If something's being compounded monthly, we're going to use this formula. N is going to be 12 because we're going to compound it 12 times a year. If something is compounded continuously, like problem 3, his IRA was being compounded continuously, then we use this bottom formula. So you kind of have to decide which one you're using in these problems. Now, when you have a problem like number 4, where he's losing 12.3% of his body weight each year, it looks like every problem on this page is continuous compounding. I don't see any annual compounding or anything else. So am I correct in assuming that all of this is going to be continuous compounding or decay? I think so. So what equation can we write for problem number 4? What is the amount he's going to weigh? It's his starting amount, which you call P. We're doing continuous decay.
So A equals 526 E to negative point. Okay. So do you always bring the decimal all the way to the front?
You'll always convert the percent to a decimal. 12.3% is 0.123. And since we're losing, it's a negative. If we were gaining 12% per year, Lord help this guy, if he was gaining 12% per year, then that would just be a positive. Since he's losing, and then T is what in this problem?
It's time.
It's 5. Because they want to know how much he'll weigh at the end of 5 years. So now, all you have to do is evaluate that. There's no taking natural logs or anything. Because I don't have a variable. In other words, my variable's over there. I don't have a variable in the exponent. And E is not a variable. E is a number. So you can evaluate that in your calculator.
Do you want me to?
Sure.
$284.38.
And it's always worth, on these, looking at the answer and saying, does that make sense? Well, actually, yeah. Gosh, he's losing 12%. He lost almost 60 pounds the first year. and then he's losing 12% of whatever that weight is the next year. So he's losing more than 50 pounds a year. In 5 years, he should lose close to 250 pounds, and that would get him down to about this weight. So this answer makes sense. It satisfies our ballpark answer.
Yeah.
All right. Let's look at the next one. An initial investment of 200 is worth 315 after 7 years of continuous compounding. Find the rate of return. So what's my equation going to be?
A equals...
And A is 315.24. And it started at 200.
200.
E to the R, 7.
7.
So the only variable in that is R, and that's what they want to know, is what is the annual interest rate on this thing. So we got to use logs to solve for a variable that's in the exponent. So what's my next step?
Put natural, or add natural log into the...
Actually, try to narrow this down as much as possible, isolate it, before you take the natural log of both sides. I wouldn't want to take the natural log of both sides with this 200 over here. That's going to mess things up considerably. So let's first of all divide both sides by 200. That is equal to E to the 7R, right?
Yeah.
Now we can take
natural log.
Now we take the natural log. Allows me to bring the 7R down there. Cross it off from there. Natural log of E is 1. So R equals the natural log of that number divided by the number 7.
Okay.
And that's the way you do all of these, is you just set up the equation and solve for the variable. Sometimes the variable is this y, the amount on the left. Sometimes the variable is t. Sometimes the variable is r. Sometimes the variable is the amount you started with. But they're always going to ask you for one of those. And the key is just setting up the equation in y equals p e to the rt format. And then plugging in everything they ask you to and solving for the one variable.
Okay, so 6.
Yeah, notice the general equation on 6 is A is the beginning amount, $1.60, times E to the RT. Okay, so we want to use that to predict when the minimum wage will reach $8.50 if the rate of growth is 3.9%. Easy enough. What do we want to do here?
A equals 1.6 E.
Now hold on. They want to know A represents the amount of minimum wage you wish to obtain, and T is in years. So they want to know when it'll reach $8.50 per hour. So this has got to become 8.5. In other words, when does $1.60 grow to 8.5 given an interest rate growth of 0.039 times t? There's your variable. In other words, solve that for t.
Okay.
First step,
Divide
Second step?
Put or take natural log of each side.
Third step?
You can put the powers.
The entire exponent can be brought down in front of that natural log of e. So if I divide that whole thing by 0.039, I solve for t.
Yep.
Now, it's kind of useful to know that when you take the logs of number, and it doesn't matter whether it's natural log or any other kind of log, when you take the logs of numbers greater than 1, you get positive numbers. In other words, the log of 1.1 is going to be positive. When I take logs of numbers between 0 and 1, that's going to be negative, always. Just useful to remember that. In other words, that is a number greater than 1, so that the numerator is going to end up positive. The denominator is positive. We're going to get a positive years for t. If you find yourself getting a negative time for t, you've done something wrong. You probably have a sign wrong or something. So it's a useful check knowing that that's a positive number and that's obviously a positive number. Okay. You want to get a number for that, or shall we go on? Shall we just get these set up and then you can end up getting the numbers later?
Yeah.
Okay. Number 7, what's my equation going to look like?
A equals 5,000 e to 6.9 times 30.
Remember to change that percent to a decimal. Otherwise, you're going to be off by a factor of 100 in your exponent. And that's going to make a gigantic difference. So what's the exponent?
0.069.
T. In other words, that's
Time
R.
is 30 years.
Oh, exactly. Sorry. Yeah. So in other words, the only variable is that.
That's pretty easy.
Yeah, you can get that out of a calculator. No need for logs or anything. Okay, how about number 8? I'll let you get those
That's
numbers.
the same thing.
Okay, so what is it?
A equals 40,000 e to the 0.0275 times 5.
Are you always in a habit of putting that leading 0 there?
No.
Me neither. I don't ever use it. Just confuses things. It's unnecessary. But most of my students use it. So I'm kind of thinking that the school system must encourage it. I don't know. To me, if I'm converting 2.75% to decimal, I'm going to put a leading 0 in there only because I know I have to move that decimal over 2 spots. So it's 0.0275. Adding that extra 0 just confuses it for me. It's going to give me a chance to be off by a factor of 10 a lot of times. So, again, you just have to solve for A, evaluate that expression. Bacteria dividing. Bacteria grow continuously. In other words, they compound continuously, like most natural phenomena. Population growth grows continuously. So a single cell bacterium divides every hour. The number of bacterium is given by the formula log base 2 of capital N equals T. After how many hours will there be 32 bacteria?
On this one, when I did that, when I got the 5, I just did it in my head for how many times.
That's,
yeah,
no, that's fine. And I know you did it in your head, but notice if we convert this to an exponential expression, what is it? It's 2 to the t equals 32. This is what you did in your head, right?
Yeah.
Yeah. In other words, I mean, perhaps you did that in your head. If you're that good with logs, some people could do that in your head. But usually you convert it to an exponential expression and then do this one in your head.
Yeah.
In other words, you don't necessarily need a calculator to do that. Do you know how to change a base? Do you know how to get this number out of a calculator if you didn't know how to do it in your head?
You just put that in.
It's the log of the top number divided by the log of the base. Like that. And it doesn't matter whether it's common log or natural log. In other words, this number that I've written over here is the same as this. In other words, when you're working with logs, the ratios are always the same. That's the same as log base 17 of 32 divided by log base 17 of 2. In other words, these ratios are the same regardless of what log function or base you're using. So when you have a change of base that you need to do, in other words, because your calculator doesn't have log base 2 on it, if you want to get this number, you have to use the change of base formula. So what would that be?
It would be log 5 divided by log 3.
Yeah, and you can use common log fine there. Or natural log. You'll get the same number if you use natural log or common log, as long as you divide. Okay. Find the maximum velocity of a rocket with a mass ratio of about 18. These are going to be relatively straightforward. They've given us the formulas. All we have to do is plug in and solve. In other words, all of these, once you get the formula written, it's just a question of solving, usually an exponential equation. But let's see, we're looking...
Plug in things.
Yeah, we're looking for V, so that's going to be our variable. C is 2.2, natural log of 18. So what is that number right there?
Here, I'll do it.
Should be 6.36?
Yeah.
So will it reach stable orbit? No, it will not. It has to reach 7.8 kilometers per second to reach orbit, and this is telling us that the maximum velocity it can reach is 6.37. So it cannot achieve stable orbit. What mass ratio would be needed to achieve a stable orbit? Well, we need this to be equal, instead of 6.37, we need it to be equal to 7.8. So we need CLNR to be equal, what did I say, 7.8?
7.8.
Okay, well, C didn't change, did that? Well, what mass ratio? Yeah, with the same exhaust velocity, 2.5. Oh, the first case it was 2.2. So in this case it's 2.5, so our equation to solve is 2.5 times the natural log of R equals 7.8. How do I solve for R?
Okay. Divide.
Okay.
0.5.
So now we have the natural log of R. What's 7.8 divided by 2.5?
It's 3.12.
Now how do I solve that?
Take the...
State it exponentially. In other words, whenever you have a log function that you can't solve, a log expression like that, try stating it as an exponential expression. And then it's going to solve itself. What's the base on this one on the left?
10.
E. Natural log is base E.
Oh.
So I could write a little e in there. Now state it exponentially. The number on the far left raised to the power of the number on the far right equals the argument, which is what we're trying to solve for. Remember, e is a number, it's not a variable, so you can get this number out of your calculator.
Okay.
Okay? There's another way to look at this. Let me just run it by you. If I say 3x equals 3, that's an equation, right? I can exponentiate both sides of this thing. And by that I mean I can take any number I want. I could say 3 to the 3x equals 3 to the 3. I could say e raised to the 3x equals e raised to the 3. I can put anything I want down here, because if I have something raised to an exponent and it's equal to the same something raised to a different exponent, then the exponents have to be equal. So if I had e raised to the 3x equal e raised to the 3, I could say that 3x has to be equal to 3. Well, by the same logic, if I say 3x is equal to 3, then I can say, well, e to the 3x equals e to the 3. Let's go back to that last problem where we had natural log of R was equal to 3.12. Well, instead of thinking of this as changing it to exponential expression, I'm just going to make both of these things exponents. So now I have e to the natural log of R is equal to e to the 3.12. Well, anytime you take a base and raise it to the natural log with the same base, this thing becomes R.
Okay.
In other words, if I said e to the natural log of x plus 2, what's that equal to?
That equals to
X plus 2.
log.
No, just x plus 2. In other words, the e and the natural log kind of cancel one another out, and you're left with just the argument.
Okay.
Okay? Same thing if I say b raised to the natural log, raised to the log base b of 17, what's that equal to?
17.
Exactly. That's a hugely valuable principle for logarithms because it then allows you to solve a lot of things by doing what we did here. Now, I didn't actually need to do that here, as all I needed to do was to know how to write this in exponential expression. In other words, back to the very beginning thing. Whoops, I erased it. But back to the thing where I said, if you start with y equal b to the x, you want to know how to write that logarithmically. Likewise, if I gave you that, you want to know how to write it exponentially. So when we had our problem, the natural log of r equals 3.12, is all I had to do was write that exponentially. Well, it's the base raised to that exponent equals that. Well, the base is e, so e to the 3.12 equals r. That you get out of your calculator.
Okay.
A rocket with an exhaust velocity of 2.4 can reach a maximum velocity of 7.8. What's the mass ratio of the rocket? Well, is all they're doing with each of these questions is giving us a different variable. In other words, we're starting with the same equation every time. They're just giving us different stuff. So they're saying that in this case, 2.4 is C, 7.8 is R,
Can't we just solve that?
Oh, hold on. Yeah, I'm sorry. R is the mass ratio. Yeah. The V is 7.8. Excuse me. And the C is 2.4, and that is what we're trying to solve for is R. So we have this equation. We have 7.8 equals.
Divide?
Yeah, that's first step, because we're trying to isolate that natural log of R. So what's 2.4 divided into 7.8?
3.25.
3.25?
Yeah.
Equals natural log of R, and now what?
You put the e's under them, and then you take...
Or just, rather than putting the e's under them, you don't really have to look at it as doing that. Just express this exponentially. How would I express this exponentially?
You'd
take the number on the far left. Now,
and
yeah, obviously I have it backwards here. So let me switch it. Same equation, but now it's a little easier to put into logarithmic expression. What's the logarithmic expression of this?
It would be 3, I'm going to have to do it in my head. It might take me a second.
No, don't do it in your head. Just take the number on the far left, raise it to the power of the number on the far right, and it's equal to the number in the middle. So it's e raised to the 3.25 equals r. R is what we're trying to solve for. So all you have to do in your calculator is look up e raised to the 3.25, and that's going to give you your answer.
Okay.
hold on. Express this exponentially.
E to the 10th power equals R.
Express that exponentially.
Where?
That's a Y.
Oh. Okay. Y equals
No.
17.
Always start with the number on the far left if the log is on the left. So it's 17 to the y power. Remember, logs are exponents. So y has to be an exponent here. Equals x.
Okay.
This step is huge, and it's not hard to memorize. In other words, as long as your log is on the left side of the equation, then you take the base of the log, which is the number on the far left, right? B is to the left of x and y. You raise it to the number on the far right, y, and it's equal to the number in the middle. All right. It looks like we're done with that page. Do you have any other problems you wanted to go over? If you like, we still have another 10 minutes. Yeah, it looks like you maybe probably have not gotten to these rules yet. These log of AB equals log of A plus log of B. You should be getting...
I have those rules.
You do? You have gotten to those? Okay.
Yeah.
Those are super important. They'll give you a bunch of exercises asking you to expand, and another exercise is asking you to compress. So let me give you one for expanding. What's that equal to?
Hold on. Okay. That. Oh, okay.
Well, let's go back. Let me put the 2 above each one. Same thing, but changes it slightly.
And do I make the base 10 automatically?
Well, these rules only work if it's the same base. So, yeah, if I don't write a base, it's automatically 10. In other words, that means common log. The only other one that you don't write the base is natural log, which is E. Every other log you have to put the base in. So if I don't write it, it's going to expand the same way to common logs. But what's the expansion going to be?
Log x squared plus log y squared.
And one more level of expansion. What can you do with these 2's?
Log xy to the 2nd power?
No, we're going to take that 2 and bring it down in front like that. Remember, that's what we did in solving all of those equations. That's how we solve for variables when they're in the exponent, is by once we take logs of them, we're allowed to bring it down and put it on the line. So that's the full expansion. Let me give you one more. What's that equal to?
That equals log the square root of x minus log to n or z.
Now what else can you Log of z, yeah. That's what that variable is z. Now, there's still one more thing you can do here, because if I write this, you don't like radical signs in log equations, so I'm going to write it using the exponent instead of the radical sign. And once I've used an exponent, now what can I do to further expand it?
Put it in the front.
1/2 log x minus log z.
Okay.
So you'll have a bunch of exercises where you have to go that way, and then a bunch more where you have to go that way. They want you to know how to expand and compress perfectly. And then you're going to use those principles to solve logarithmic equations. And that's really where logs end. They will end for you is once you get to that point. So.
Okay. Well, we're going to have a test on Wednesday.
Uh-huh.
So I could talk to my teacher and get a test review.
You want to schedule an online session before Wednesday?
Yeah.
Let's look at my calendar here. Monday and Tuesday both work. Monday anytime after 6:15, Tuesday anytime after 5:30.
Let's do Monday.
At what time?
Anytime after 6:15?
Yeah.
I guess 6:30.
Okay. Let me put it in there. And what's your phone number, Caleb? Because
303
uh-huh.
667 5064.
Because after the first session, what I generally do is just text you the meeting ID number.
Oh, okay.
And you will notice that you probably have that icon on your desktop. If you take a look at your desktop real quick, do you have an icon that looks kind of like this flower?
Yeah.
Okay, well, whenever you want to join GoToMeeting, just double-click on that icon. It'll ask you for a meeting ID number. I will have texted it to you. So all you got to do is put it in, and we'll be in a meeting.
Cool.
Okay? So I will do that at 6:30 on Monday night, and I will talk to you then.
All right.
All right, Caleb. Nice working
Thank you.
with you. Talk to you Monday. Bye-bye.
Okay.